Assalamu alaikum. Today we are going to talk about capacitance and capacitors. We are going to derive capacitor and talk about the significance of capacitance in context of electromagnetic theory. First, let's consider this case where we have two conductors or two metallic bodies which are embedded inside some dielectric. Now, if I told you find the electric potential due to these two conductors, as we all know that the outer surface of each conductor of these is equipotential surface. Okay, so to find the electric potential, we want to find the difference of the potential between this conductor, the positive one, and the negative one by this equation, by taking the line integral of the electric field along the path between this conductor and this conductor. Okay, this is the path between them. And as you all see, the electric potential is dependent of the electric field. Now, how to find the electric field? The electric field in this case cannot be found by Gauss's law because these two surfaces are arbitrary. Okay, there is no symmetry. We can't construct a Gaussian surface around any of these conductors, so we are going to use Coulomb's law. And this is Gauss's law. Okay, the electric potential is going to be normal to the surface of this conductor. Okay, and this can be found by this equation: 1/4 pi epsilon. This epsilon is the absolute permittivity, is equal to the relative permittivity of the dielectric times the permittivity of the free space, and the line integral and the volume integral for the charge density divided by the square distance. Now, if I told you that we doubled the charge on each of these two conductors, okay, what will happen in this case? If we double the charge on these conductors, also the charge density is going to be doubled. And if we double the charge density, the electric field also is going to be doubled because its function is dependent of the charge density. Okay, and it's going to be doubled by taking into consideration that that this dielectric is linear. Okay, by doubling the electric field according to this equation, the electric potential is going to be also doubled. Okay, and by watching this flow, we can deduce that doubling the charge on each conductor is going to also double the potential due to these two conductors. Okay, I'm sorry for adding this vector notation. The electric potential is a scalar quantity, it's not vector. Anyways, doubling the charge is going to double the electric potential, so that we can deduce that the charge density, that the charge is linearly proportional to the electric potential. Okay, and we can determine this by this equation, by this simple equation: Q times C V, as C is the proportionality constant. Okay, this proportionality constant is known by the capacitance, and the capacitance is the ability of the capacitor to hold charge per volt, and this is capacitor. Okay, it's simply a system of two conductors. Each one of them holds the same charge upon it. And it's worth mentioning that capacitance depends on the geometry of conductors, geometry of these two conductors, meant by the shape, the size, and the mutual position of each conductor, and the permittivity of the medium between them. And in this case, you may notice that to find the capacitance, we simply use this relation Q divided by V, where Q is the charge of each conductor when the charge on both conductors is equal, and V is the electric potential due to these two conductors. And if I told you to find the capacitance of an isolated metallic body, what can we do? To find the capacitance of a single conductor of an isolated metallic body, we simply use the same relation Q divided by V. In this case, we assume that our body has the charge of plus Q, okay, and the second body, which carries the charge of negative Q, exists at infinity, so it has no effect to the potential due to this single conductor, because the potential at infinity is equal to 0, as the infinity is assumed to be the reference point. That's the end. See you.